thin film of soap water appears green when lit from above. Calculate the thickness of the film, assuming the green light has a wavelength of 500 nanometers. Assume that this is the thinnest film that can produce green light. To gain a deeper understanding of the process of thin film interference, we need to understand two basic aspects of this process. This diagram will help clarify those aspects in which the thin film exists between the two black lines and light comes in from above via an index of refraction n1. It will make its interference via the thin film of index of refraction n2, and finally there is some medium that is sometimes called the substrate, which we'll consider to have index of refraction n3. Primarily we consider the case in which the incoming light is perpendicular to both of these surfaces. However, since that's difficult to draw in a diagram, we're going to give the light ray itself some small amount of tilt. At the first surface there will be a reflection, which follows the laws of refraction. Angle of incidence equals angle of reflection. Also there will be a transmitted ray, which has a possibility of reflecting off of the bottom surface and then transmitting through the top surface. These two outgoing red arrows are the ones that we consider to have interference, and we need to understand the conditions that lead to either constructive or destructive interference, assuming that the soap film has some thickness d. Two important aspects deserve our consideration. At each reflection we might flip the wave. And what flip means is that an incoming crest of the wave upon reflection would become a trough, and vice versa, an incoming trough of a wave would become a crest under reflection. We figure out whether we have the case of flip or no flip under reflection by examining the index of refraction of two different media. One is the index of refraction on the incoming side, and the other is the index of refraction of the medium that we are reflected from. We generate a flip whenever the incoming medium has the lower index of refraction, and we don't flip when the incoming medium has the higher index of refraction. I find it convenient to remember what happened with musical instruments, where musical instruments had either closed or open ends, and we can make the analogy that the closed end is when the reflected medium has a larger index of refraction, and an open end is when the reflected medium has the smaller index of refraction. The second item that we need to consider in figuring out whether we have constructive or destructive interference, here the extra distance due to a round trip inside the film effectively slides the second wave as compared to the first, which can again cause crest to meet trough or crest to meet crest, depending upon the extent of the slide. These two factors, accounting for the flip that one experiences upon reflection, as well as the slide due to the additional round-trip distance, will allow us to determine definitively the condition on D that results in either constructive or destructive interference between these two outgoing rays. I find it most convenient to summarize these conditions in the form of a convenient table. The rows of this table decide whether we have an even or an odd number of flips of all waves considering both surfaces, and the columns are used to decide what condition on D will result in either constructive or destructive interference. Because a round trip requires going down by a distance d and back up by a distance d, each one of these conditions will be placed not upon d, but as a condition on twice d, because that's the round trip distance. The easiest way to begin filling in this table is to look for the zeros. Let's consider the first row. If we have an even number of flips, either 0 flips because we didn't flip at either surface, or 2 flips because we flipped at both of them, then in this case the natural tendency of the waves is towards constructive interference. Therefore, the zero distance result would be constructive interference. For an odd number of flips at one surface or at the other surface, but not at both, the natural tendency of the two waves is to have crest meet trough, resulting in destructive interference if there is no slide of the waves along one another. At this point, it becomes very easy to complete out the table, because what we'll see is that if our twice d round trip gained us wavelength over n2, because the light is in the medium n2, or twice this amount, or 3 times this amount, etc., all of these are conditions for constructive interference with an even number of flips. We can similarly list the conditions for destructive interference under an odd number of flips. Finally, we recognize that since the integer lambda over n2 terms have been filled in each row, the half integer quantities will fill up the remainder of the table. So we'll have half lambda over n2, 1.5 lambda over n2, 2.5 lambda over n2, and so forth for the destructive interference under an even number of flips, and these same quantities result in constructive interference under an odd number of flips. We will use this table in every problem of thin film interference with the light coming in perpendicular to the film by first deciding which row is the condition we are under and whether we are looking at a condition of constructive or destructive interference. This will then yield for us the single equation we need to determine the distance d of the film. Let's go back to the problem at hand. In the current problem, we have a soap film, and that means that the three layers are air, soap, and air, meaning that the indices of refraction are 1.0 in both regions with air and 1.33 in the region of the soap film. Investigating the first reflection, we see that since we are in air and we are bouncing off of soap, there will be a flip at this surface. However, at the second surface, the light is in soap, and we are reflecting off of air, and that means the second surface results in no flip. This is one flip total, and 1 is an odd number of flips. The next thing we must investigate is the wording of the problem, and we see that this soap film appears to be green. Because it appears green, this means that the green light is undergoing constructive interference. So, referencing the table that we formed earlier, we will go to the odd row and the constructive column and thereby find that the formula for the round trip distance is the half integer formula. And this is the one that we will copy into our problem at hand. Finally, we notice that this formula gives us options. 2d might be half lambda over n2, it might be 1.5 or 2.5, and we need to again reference the problem to decide how the language of the problem limits us to be choosing one formula and one formula only, and this language occurs in the last sentence where we are to choose the thinnest possible film. The thinnest possible film means the smallest value of d, and therefore we will take the leftmost term out of all these possibilities, so we find that our situation is given by twice d is 1/2 lambda over n2. The light in question for us is 500 nanometers, and N2 represents the index of refraction of the thin film itself, which is 1.33. This allows us to solve for the thickness of the thin film being 94 nanometers. The next time that you see someone blow a bubble out of soap film and you see a region that appears to be green, it might very well be 94 nanometers thick.